Okay, so we're looking at some writing in sigma notation. So we're given a sum, we just want to write it in sigma notation. Clearly it looks like we're going from 1 to 8, so I'm just going to write my big sigma symbol here. I'm going to go from k equals 1 to 8, and it looks like I'm just cubing all the numbers from 1 to 8. So that would be n cubed. So that one was pretty straightforward. The next one we have the numbers, these are all odd numbers stopping at 23. So to me, odd numbers, the only difference between odd and even numbers is a difference of 1. So if I take 2n and minus 1, that's pretty much going to give me any odd number I want. So if I plug in 1, if this is a sub n, if I plug in 1, I get 2 times 1 minus 1, which gives me 1. And if I plug in 2, I get 2 times 2 minus 1, which is equal to 3. And if I plug in 3, I get 2 times 3 minus 1, which is 5. And here are my odd numbers. So therefore, my sigma expression is going to be k equals 1 to 2n minus 1. That is my expression. You would think that 23 would go up here. However, it does not, because a of 23 would be 2 times 23 minus 1. So this is 46. Minus 1, which is 45. Wrong. Our last term is 23. So if this is our term that we're talking about, what is the n? What term number is 23 if our last term is 23? So what is the term number that corresponds to 23? So 23 equals, this is my expression that generates all my terms. So can I figure out the term number by solving this simple equation? So adding 1 to both sides, I get 24 equals 2n. So n equals 12. So therefore my term number in this case is going to be 12, just by solving that equation. This next one is also to write it in sigma notation. Notice that this last term has a negative 1, like a previous problem that we did. And we have a common ratio of 2/3. So what's 2/3 times 2/3 is 4/9. 4/9 times 2/3 is 8/27. So clearly, for our sigma notation expression, we're going to have a 2/3, and we're going to have a negative 1, and we're always going to start at 1. Very few sigma notation problems don't start at 1. And we want to make it so that my last term on negative 1 is 12, and on 2/3 is 11. So if that's the case, if I end at 12, that means negative 1 has to end at n, and 2/3 has to end at n minus 1. Let's check it. So if a sub n is equal to 2/3 to the n minus 1, negative 1 to the n, a sub 1 would be equal to 2/3 to the 1 minus 1 times negative 1 to the 1. So that is equal to 2/3 to the 0 times negative 1 to the 1, which gives me negative 1, which doesn't give me 2/3. So it looks like my exponents here are messed up. So let's try a different set of exponents. Let's make this just n. And if I want this one to be 11, so that means I don't want to stop at 12 anymore. Let's stop at 11. So now I have 2/3 the 11th. That's what I want. I want negative 1 to the 12th power, so that would be plus 1. So this didn't work. So if my nth term is 2/3 to the n, negative 1 to the n plus 1, a sub 1 is 2/3 to the first, negative 1 to the 1 plus 1, which gives me 2/3 times negative 1 squared, which is equal to 2/3. Let's try the third term right here. A sub 3 is 2/3 cubed, negative 1 to the 3 plus 1. So that's equal to 8/27, and this is negative 1 to the 4th. So that's 8/27, and that's a check. So this is our sigma notation that generates this sum right here. Okay, so let's look at this last one. Let's find the 6 terms of the sequence and then determine an explicit function n. So this is a recursive function because the nth term is determined by the previous term. An explicit function just means that you can just take a number, plug it into it, and you'll get a value. Just like here, I took 3, I plug it in, I got the value. I didn't need to know the second term to get the third term. So that's in a recursive sequence, is you need to know the previous term to get the next one. Explicit one is you can just plug in a number and you get an answer. So a sub 1 is 1. A sub 2, according to my definition, is 2 times a sub 2 minus 1, which is 2 times a sub 1, which is 2 times 1, which is 2. A sub 3 is 3 times a sub 3 minus 1, which is 3 times a sub 2, which is 3 times 2, which is equal to 6. A sub 4 is equal to 4 times a sub 4 minus 1 equals 4 times a sub 3, which is 4 times 6, which is 24. A sub 5 is equal to 5 times a sub 5 minus 1, which is 5 times a sub 4, which is 5 times 24, which is equal to, how can I do that in my head? 120. And we want to know the sixth term. So the sixth term is equal to 6 times a sub 6 minus 1. 6a sub 5, so 6 times $1.20 is 720. Let's look at the graphing calculator. So let's clear this out and let's clear out the history. Let's go back to sequence mode because we're dealing with a recursive sequence. This goes back to y equals. Our definition is n times the previous term, parentheses, n minus 1, close parentheses, and our first term is 1. So notice it puts the curly braces in there for you after you press enter. Let's do our table set. I want to start at 1, not at 6. And here are my table of values. So 1, 2, those are all the numbers. So the seventh one is 50, 40, 40, 30, 20. So it gets rather large, rather quick. So I just wanted to review using the graphing calculator to do a recursive sequence. And note, usually when I'm done with recursive sequences, I go back to function mode, because that's normally the things that we're working with. And notice when we go to y equals, we're y in terms of x. When I plus this button, it's the first one, which gives me an x. Just a little tip from me to you. Okay, so the question is, how do you write this as an explicit function of n? Here's a challenge to you. If you're the first person to email me with the answer for how do you write this as an explicit function of n, meaning you plug in any number you want and you can get the value. So in other words, if I plug in 4, how do I get 24 without having to know the third term or the second term? So if you're the first person, I'll give you a free homework assignment.